Welcome everybody to our free electrical safety and lockout tagout hazardous energy training series. We do this about every 6 weeks. So today's topic is establishing electrically safe work conditions. We're going to do a deep dive into Article 120.6 of the NFPA 70E. What are the actual steps you have to take before you can take off your PPE? With us today, we have a special guest, Alan Bond. He's with Panduit, and so he's going to be talking about another option for verifying electrically safe work conditions later on, those permanently mounted test devices. So we don't talk about those nearly enough, I don't think. I know I mention it pretty much every training I give whenever we have like a full training, but it's not nearly talked about enough. So my name is Caitlyn Wininger. If you don't know me, I'm an electrical engineer here at Herzig Engineering. I've got my CESCP, so Certified Electrical Safety Compliance Professional through NFPA. So by all means, if you guys have questions, do not hesitate. Use the question box or the chat feature that you're seeing in GoToWebinar. That's how you're going to be able to interact with us today. Alan, why don't you tell us a little bit about yourself?
Yeah, absolutely. I'm a mechanical engineer by degree, but right now I am the global product manager for Prevention Through Design, which is one of our groups here at Panduit. And we focus on, this is what it sounds like, prevention through design, developing products to prevent hazards through the design of a product or process. So been here about 2.5 years or so, and VeriSafe, as we'll be talking about later, is one of my main products. So.
Very good, very good. So we got the right person on the webinar today for this.
We'll see. Yeah.
I'm sure it'll be great. All right, so we got a couple of poll questions to get us started. First off, I just want to get a feel for what do you guys know about electrically safe work conditions? So do you know how to establish an ESWC? The options are yes, that you're confident in that process. Yes, you're pretty sure how to do it, or no, you're not certain what the steps are. Go ahead and click your answer and submit that poll. Results, perfect. We're getting some responses in now. All right. pretty even split so far, but it's still bouncing around. Just give it another 10 seconds or so. Just click on your response and click the submit button. All right, we'll go ahead and close this out. Let's share the results. Okay, so only 16% of you are confident you know what the steps are for verifying an electrically safe work condition. So good for you guys. Hopefully you can still learn something new today. The rest of you are pretty sure, so we'll solidify that for you, or that you're not certain at all, which is totally fine. You got to start somewhere. Let's dive in and learn this. And then the other question I had for you before we get too far is, do you have any permanently mounted absence of voltage testers? And just click not sure if you're not even sure what those are. But yes, no, not sure, select your answer and submit it. It's just another way to, well, check for voltage before work. We'll dive into that quite a bit. So yes, no, not sure. Do you have any permanently mounted absence of voltage testers? Okay. Yeah, there's one response definitely taking the cake. They've been around for a while. This isn't a necessarily new technology, right?
2017, Q4 of 2017 is when we first released.
So relatively new, but not brand new.
Right.
All right.
Definitely older products out there.
Yeah. Okay, I'm gonna go ahead and close this out and show the results. So pretty good split between yes and not sure. The rest of you are just like, nope, we don't got them. So hopefully today we can explore that option and explain, why I'm bringing that up and why we have Alan here today. It's not that you have to have them by any means, but they do have some pretty cool features to them, and they make things pretty helpful. All right, so we do have some different topics that we're going to cover. First, I'm just going to go through what the steps actually are in the 70E, and then we're going to kind of step aside and look at other compliant methods for establishing safe work conditions, so looking at the exceptions in 70E and the options for those a little bit more, and then we'll summarize with the typical how do you get started today and how we can help if you need any of it. And then we'll open it up for questions and discussions. However, if you have questions, please do not hesitate to submit it throughout the presentation. I have that question box open and I am monitoring it as we go so that we can try to answer any questions as they come up, so that it's while we're talking about that specific thing. Otherwise, you can hold them to the end, that's fine too. But usually better just go ahead and submit it so you don't forget. All right, so let's dive into those requirements. How do we get an electrically safe work condition? Well, what's the purpose of that? Frankly, all electrical conductors or circuit parts are considered energized until verified to be de-energized through the process of achieving an electrically safe work condition. In other words, unless you can complete the steps outlined in the 70E, you have to act like it's energized work. All right, so you have to keep your PPE on, you have to have the boundaries set up, you may have to have a second person depending on the task and your company's policies. There's all sorts of things that could be at play, potentially even an energized work permit if you're servicing it without verifying that it's off. Don't want to have to go down that rabbit hole for the vast majority of tasks you do. So let's just break down how we actually get it in a safe work condition and can work without all those extra hoops. Okay, so we're looking at Article 120.6. Let's dive in. First is just determine all possible sources. Figure out where the power is coming from, which is kind of like a no duh. If you're going to shut it off, you have to know where to shut off the disconnect switch. You can look at panel schedules, equipment labels, one-line diagrams, whatever you have available at this point, as long as they're up to date. A little sidebar here, please update your labels and your one-lines and your panel schedules, because they're totally useless if they tell you stuff that happened, 5 years ago and now it's all changed. Let's go ahead and get it updated.
Potentially add additional hazards as well if they're incorrect. So yeah.
Yeah, that's a good point too. Additional hazards, maybe it's a totally different result for your arc flash study now and you don't even know it. Could be different shock hazards. I've seen enclosures that said 208 volts and actually it had been refed and it was now like a 600 volt because it was an international piece of equipment that had been installed, but they didn't update the labels. It was just a whole mess. So yeah, you don't want to take anything for granted. Good point. Okay, step number 2 is kind of 2 separate steps in my opinion. You properly interrupt the load current and then you open up the disconnecting devices. All right, we want to shut the equipment down. The motors need to come, stop drawing current, and whatever loads you have need to be turned off with the proper controls, push buttons, switches, whatever. And then you go open up the breaker or the disconnect point, because the rating of some disconnects are not designed to interrupt that load current. So if it's still drawing power while you make or break a circuit, it could have some electrical arc over. And it's not a matter of if, but when you do that too much or there's too much current being drawn, it'll actually arc over enough that you could have that potential of an arc flash. It could ionize the air around it, it could cross phases, it could cause a whole lot of different problems there. So make sure you isolate that power first you shut down that equipment first before you open it up to isolate with the disconnecting point. Okay, step number 3, moving right along. Wherever possible, visually verify that all blades of the disconnecting device are fully withdrawn or that draw-out type breakers are withdrawn to the fully disconnected position. In other words, if something's broken, we kind of want to know that ahead of time. Right? So if you can, at this point, you do still need to wear PPE because, well, the line side at least is still going to be energized. But if something broke or came loose or the handle isn't even connected to the rest of the bars at that point, seen that happen before. Yeah, let's get some eyes on those, see that the blade's disengaged. Now, I've heard some people argue that if you can get eyes on the disconnect point and you see that it's disengaged, then you don't need to verify absence of voltage. And I'm like, what? I'm sorry, 2 things. Number 1, what if that was the wrong disconnect and it was mislabeled or whatever, right? You could absolutely still be exposed to hazards. And number 2, what if there's backfeeds that you're not aware of, or there's a fault in the system? Or No, you still have to verify it's off even if you see that the blades are open. But if you can, go ahead and visually verify. Not always possible to do that. So step 3 to establish an electrically safe work condition is to visually verify if possible. When is that not practical? So an option could be that it's high priority and you need to work quickly. Arc flash label indicates higher calorie per centimeter squared of a hazard than your available PPE, or you used an e-stop to shut down the power. Okay, 2 of those answers, hopefully you're looking at it and going, what? That's not even realistic. There's no way. So process of elimination, let's see what you get. Okay, starting to get some responses here. Give it just a couple more seconds. All right, so most of you got it right. If you don't have PPE rated high enough to open up an enclosure to look at the disconnecting points, you're probably not going to be the one to open it and visually verify. So maybe you need to get someone else to help shut it down if you're worried about condition of equipment, if you're worried about not being able to visually verify. Otherwise, you can just move on. The last one though, an e-stop used to shut down the power. So oftentimes, I don't think e-stops really shut down the power. They stop the moving components. I've seen that plenty of times. If your e-stop does actually shut down power, great for emergency situations, not for verifying an electrically safe work condition. You actually have to physically isolate that disconnect point, and an e-stop is not designed to do that. Okay, so we'll go ahead and go to the next step. So visually verify if possible. Step number 4 is basically release stored electrical energy. So if you've got like capacitors or something and you need to let them bleed off, let's go ahead and do that. Release or block stored mechanical energy, or really just anything that's not electrical, so that they cannot be unintentionally energized by such devices. So in other words, like a motor, think about them being able to turn and that start to induce a voltage. Let's not allow that to happen while you're working. And then apply lockout tagout devices in accordance with your documented and established procedure. So this is one thing you have to realize: we don't always work in a bubble. Maybe electrical isn't the only hazard you have to face. Think about it. There's of course electricity, live and stored, both, active and stored energy. Mechanical parts, often there's moving parts inside of equipment or nearby. Maybe you've got an assembly line or a belt system that's near your control panel that you're working in or whatever. Make sure that those aren't going to be operating and hazardous and you're within a pinch point area. Maybe some hydraulics, pneumatics in the area that you have to worry about, depending on what you're working on. Of course, thermal, maybe you need some time for that equipment to just cool off before it's safe enough to approach and get in there. Chemicals, natural gas, active or stored energy, as in like springs, for example, and gravity. People always seem to forget gravity.
Yeah, a couple common applications are brake presses and robotics, right? As soon as you remove that power, that brake press might stay up. The robotic arm might stay in place.
Might, yeah, that's kind of a big gamble to take though.
Right, absolutely, absolutely.
Yeah, so don't neglect, I should say, the other options as well, the other potential hazardous energy sources.
I do not trust my hydraulic jack when I get underneath my car.
No, exactly.
Fixed jacks there, yeah.
Yeah. Now, when it comes to being a qualified person, and we had a whole nother webinar about being qualified and what it takes to actually become a qualified person to do electrical work. Qualified and authorized, they're two separate terms. Okay, there's authorized personnel for lockout tagout, and then there's qualified personnel for electrical work. Not all authorized personnel are qualified. but all qualified personnel need to be authorized because they have to be able to establish an electrically safe work condition. Part of that's lockout tagout. The difference is someone who's authorized but not qualified can't do step 7. All that to say, has to be a qualified person in order to do step 7 here. That's where that splits off. So if you're going to open up and expose anything, electrical conductors, circuit parts, 50 volts or greater, by and large, sometimes there's unique situations, but 50 volts and greater, then you have to be able to use a meter to test for absence of voltage. That is truly whenever you start to know it's safe. Okay, and there's too many stories out there where people shut it off and they lock it out and then they get to work and there's something wrong and something's still energized and they may or may not survive to tell the tale themselves. So super, super critical point here. Use an adequately rated portable test instrument to test each phase conductor or circuit part at each point of work to test for the absence of voltage. So that is a change in the 2024 edition of the 70E. It's specified at each point of work. I think it was more just a clarification. That's always what was meant, I believe. But there's a lot of people who would, like a knife style disconnect, for example, they would turn off the disconnect switch and they'd open the door and they'd do their visual verification. Great. And then they think, oh, well, I can do live, dead, live right there. The load side of that disconnect is off. You're right. But what if that was the wrong disconnect? What if there's a backfeed? All the same things that I pointed out for the visual verification. Okay, so where you're going to be sticking your hands, that needs to be verified to be off. To do that, you're going to be testing each phase conductor or circuit part, both phase to phase and phase to ground. I've seen plenty of times where somebody goes in and I'm on site doing an audit or a walkthrough or whatever, and somebody puts, a lead on ground and then they probe everything and then they walk away. They're like, okay, it's safe. And they didn't check phase to phase. It's a very, very common mistake. Go ahead and do that as well. Before and after each test, determine that the test instrument is operating satisfactorily through verification on a known voltage source. In other words, make sure your meter's still working. So it's a live check, then you check phase to ground where you're working, back to the live known source and get a reading that you would expect. We'll dive into that just a little bit more in a moment, but for now, the meter, double check first of all that it's the right rating. Okay, there's also times where putting leads on equipment, if it's not properly rated, could be the cause of an incident. So have a good category rating. Most often Cat 3 600 volts is what we see people need. Cat 3 1000 is even better, Cat 4 600, Cat 4 1000, but minimum Cat 3 600 volts. And then check your leads as well. Make sure they're in good condition while you're doing this test. You don't want any exposed metal or nicks or broken handles, such and so forth. And they also need a proper rating. And it seems kind of silly. Number 3 is pointing to the dial there. It's got 3 options and an off. Make sure it's on the right setting though. It really is so easy to accidentally turn it one setting too far. Or on the other hand, you have some pretty complex meters out there with a bunch of functionality and a bunch of buttons. And it's really easy to fat finger it and end up on the wrong setting. If you put leads on equipment on the wrong setting, it could cause problems. Maybe it would just damage your meter, but maybe worse. Okay, so make sure you got the right tool for the job and then do that live, dead, live check. Okay, so in this example, the triple check is like a known outlet, like a 120 volt outlet. Okay, so we've got 119 is what we're reading. 118, 121, somewhere in that nominal range. That's an acceptable, expected reading to get. And then you go to where you're going to be working, where you're actually going to stick your hands in and get 0 for everything. Live, phase to phase, phase to ground, everything. And then go back to that same known source and you should get the same rating. If you get a drastically different reading or no reading at all, that's a sign that your meter has malfunctioned and you should not trust that 0 was actually 0. Okay, so I know a gentleman personally that this saved his life. He was doing troubleshooting on a piece of equipment. He figured out what was wrong with it. He went to shut it off. It was funny, the only outlet in the room was being used for a couple box fans because it was so hot in there. And so he unplugged one of the fans and he was doing his voltage check and he got what he expected for an outlet, plugged the fan back in. He's got his PPE on and he's checking phase to phase, phase to ground. Everything's good. It all says 0. He goes back and unplugs the fan again, and the outlet's reading 0. He's like, what? So he plugs the fan in, it still turns on. Obviously there's power there. Tries again. He's like, okay, nope, my meter's not reading it. He wiggles it around. He's like, maybe I'm not getting a connection. Nope, can't get it reading. It is, meter's just stuck at 0. So he calls up a friend and he's like, hey, can you come here and bring your meter? Borrows it, goes through the same process, checks phase to phase to ground, and it turns out one of the phases was still energized. And for some reason, he thinks that whenever he was testing that phase, maybe there was a transient, maybe there was a spike in the current, we don't really know. It damaged his meter, it malfunctioned, got stuck at 0. And if he had trusted that 0 was 0 without verifying the meter worked, he very well could have just taken his PPE off, stuck his hands in, and maybe gotten shocked or worse. Okay, so this is life-saving stuff.
Yeah, that second live is important.
We're putting our lives in the hands of an electronic device.
Yep.
Let's make sure it works, okay? And if you don't have a good known voltage source in your area, there are proving units. They make them. You don't have to get this. I mean, it's definitely not required to use, but they are super handy to carry around, especially if you have to do this quite often by hand, mind you. This is the by hand method.
Right.
Okay. So it's got AC or DC on this proving unit, and then you just put the leads in, super low current. There's no hazard for you here. It's just you're getting that voltage check, 240, 242 volts, whatever. You got your known source. And when you're doing that phase to phase and phase to ground, like I said, do it all. A to B, A to C, B to C, A to ground, B to ground, C to ground, and if you're at a surface entrance, neutral to ground as well. Okay, so that's step number 7, live, dead, live, phase to phase and phase to ground with a meter. There is an exception if you have an adequately rated permanently mounted absence of voltage tester. It does have to be permanently mounted and installed properly. Okay, it's per the manufacturer's requirements, and have it connected to all the circuit parts that are going to be needing to be tested to. It's listed and labeled for that purpose, and it will do the same thing that you would have done by hand. In other words, it will test each phase conductor or circuit part, both phase to phase and phase to ground, and has its own ability to do the live, dead, live portion of that. So it has something to test itself to make sure it's still functioning. So for example, the 2 options there for step number 7 is using your portable test instrument. That's probably the by far still most common method that people use. And I'm not saying you can't, it's just, it does take a little bit, and you have to suit up. You have to be exposed to those potential hazards, because there's no guarantee it's off until you verify it's off. So you have to suit up, you have to go through that process by hand. There are absence of voltage testers, such as FaraSafe, which is what we're going to be talking about today, that kind of take out a lot of those additional steps and removes the exposure piece. You don't have to open it up until you know it's off, which is actually really cool. I tend to bring these up and these kinds of things up whenever I see like really dangerous equipment. Like if the results of a study is over 40 cals per centimeter squared and they only have 40 cals available, I'm like, all right, next time you have a shutdown, you really should get one of these things installed. Especially after like the utility, we don't have control over their protective devices, so there's not much we can do to help lower the hazard at the mains of your equipment. That's my number 1 place that I would suggest putting these kinds of things, but you can put them everywhere. Frequently accessed equipment, the more often you have to do this live, dead, live check, you push a button, it'll do it for you. We'll get into that more, but I'll let Alan explain that a lot more. He knows more about that stuff. There is another exception. So exception number 2 is about if it's over 1,000 volts. So we're talking more like medium voltage equipment at this point. You're not going to use like a physical meter with the metal leads on the equipment. It's more going to be a capacitive test instrument that's non-contact, a proximity detector, for example, a nice rated one that's designed for absence of voltage over 1,000 volts, not these little pen testers. Those are very different. Do not use these for verifying absence of voltage. I always have to clarify that because people get those mixed up. It's so easy to do, especially if you carry these around. I'm not even going to get into whether or not you should carry around these Widowmakers. Okay, but if you do, don't use them for verifying absence of voltage. All right, so we talked about step number 7. Now step number 8, which is the final step listed in the 70E. If there is a possibility for induced voltage or stored energy, backfeeds, things like that, you're going to ground out all the circuit parts before touching them. Or if there's a chance that you could have them re-energized, go ahead and ground them out as well. These steps to making sure that they're placed in the right locations and that they have a high enough capacitance to handle all the fault current and a low enough impedance to immediately cause operations of protective devices. All that information is in ASTM F855. More often than not, I see this in medium voltage applications as well. Not always, but that's more common. Okay, to summarize, here are those 8 steps. Determine all sources, turn off your equipment, and then open all disconnects. Release stored electrical energy, release or block stored mechanical energy, apply your lockout tagout, do your live dead live check with your meter or with another device, and ground if determined necessary. Again, this is only going to be done by qualified electrical workers for 50 volts and above. And I did have a question here, is the cutoff the same for AC and DC? And as of this version of the 70E, yes. So it's 50 volts across the board. And then, my next question here that came up, when do you need PPE on? Which is great because my next polling question actually was going to test to see if you guys could answer it. So at what point can a worker take off their PPE to complete an electrical task? After the disconnect's in the off position, after locks and tags are in place, or after verifying absence of voltage and applying temporary grounds if needed. All right, getting some good answers in here. Most everybody's getting the answer here. Okay, go ahead and close it out. And I'll share the results. So most everybody got it right. You have to verify absence of voltage and apply grounds if necessary before you can take off your PPE and get to work. Just because locks and tags are in place does not necessarily mean that it is safe to work on. You have to verify that it's off with your meter. That is the key pivotal factor. All right. So what are some other compliant methods? So we talked about that live dead live check. We spent a lot of time talking about, making sure you know how to do it by hand. But then there was that exception that you could do it with a permanently mounted absence of voltage tester. Okay, so that is where stuff like this could come in. There are a lot of options out there, but Alan Bond was generous enough to give his time today to talk about one option that is on the market here. It's Panduit's VeriSafe. So I'm going to actually go ahead and play a short little video that will introduce what this is, how it works. It's just a couple minutes long. How it helps you, how it saves a lot of time and exposure to hazards, and then I'll let Alan take it from there.
You asked, we delivered. Panduit, the experts on absence of voltage testing technology, developed the next generation VeriSafe AVT, continuing to provide our customers with increased electrical safety while simplifying the testing process. The VeriSafe AVT's primary functions include voltage presence indication to show when electricity is present, and absence of voltage testing, providing a green light when the test point is de-energized. If the absence of voltage is not confirmed, diagnostic codes indicate why. AVTs can now be used in even more locations throughout your industrial or commercial facilities, from power distribution and electrical infrastructure, to to automation and motor control. Use AVTs anywhere your employees need to test for absence of voltage. 2.0 AVT is designed with flexibility in mind. You select the options that best suit your needs. All VeriSafe AVTs test for absence of AC and DC voltage. The 2.0 AVT supports 2 indicator modules, allowing the test to be initiated from more than one location. Put extra distance between the operator and the hazard by installing the second indicator at the entrance to a controlled area or outside the arc flash boundary. Integrate the AVT into your control system, utilizing Safety Integrity Level 3 solid-state contacts or an Ethernet connection. Monitor voltage status and troubleshoot remotely with the optional network module. Safeguard your employees, your equipment, and your bottom line with a family of products utilizing VeriSafe's groundbreaking electrical safety technology. Operate faster, smarter, and safer with VeriSafe AVTs.
All right. Stop showing the video. There we go. Okay, so with that, I'm going to go ahead and pass it over to Alan.
See if we can get this right.
There we go. Okay. Sorry, I have to give your controls over. Okay.
All right. Let me show my screen. How do I, which screen do you see right now?
We see the PowerPoint. So not the display or like the presentation mode, but like where you can edit it.
Got it. Let me turn it off. I wonder if I can select which screen to see here. Should have checked that. There we go. Okay, I see it now. Screen 2. I assume now you see all of us, or all of me.
All of that screen, yes.
All that screen, yes. Okay. Let me swap here a little bit.
Perfect. There you go.
You see all the other junk in front of it or no?
Nope.
Okay. I got all the webinar stuff there. So, all right. So thank you. There's a lot of information there. There's going to be some redundant information, but I think it's going to make sense. I'll kind of cruise through it pretty quick because Caitlyn already went through it in very good detail. So thank you. So VeriSafe. VeriSafe is the absence of voltage tester, as Caitlyn pointed out, is a different method to confirm the absence of voltage. And so when you think about the hierarchy of controls, it's not PPE, right? It's not an administrative control like work instruction or signage. It's more of an engineering control, which is designed to isolate hazards from people, right? It's not substituting the electricity or eliminating the electricity. It is controlling, the exposure. So getting into the process real quick, like I mentioned. So putting up the barricades, applying notifying affected individuals, folks nearby that you're going to be opening this panel that might have hazardous energy in it, right? Determine all sources, right? Disconnect the breakers, go through and apply your locks and tags, putting in your PV, selecting it, inspecting it, and so on. And then getting into the bread and butter of the inspecting and then checking your meter, going in and checking your panel, both phase to phase ground. So 6 measurements, 7 with that neutral ground if it's a service entrance, as Caitlyn pointed out, and then going back to that same convenience outlet and confirming that your meter is working both sides of the measurements, right? That live, the bookended live, I'll say, is important to get both sides. It's not just a live dead test, it's a live dead live test. So at that point, as long as all those results panned out appropriately, then you can confirm and say that, hey, it's safe to pull off my PPE and go in there and see what I'm doing and do whatever work you're looking to do. Can be quite complex, right? A lot of human error in there. So that is one of the things that VeriSafe comes to improve. So
that's a really good point. I just want to make, I've seen people do the live dead live check and try to do phase to phase and phase to ground. They were giving it their best shot, but the connection points had those silly little touch safeguards. They're not silly, they're great. They're helpful for incidental contact, but it made their leads not actually reach all the way in and make contact.
Yeah.
And I was like, all right, you're going to need different leads or you have to take the cover off. And they didn't even think about the fact that their leads weren't making contact. So yes, even if you do all the steps right, there is still a chance of missing something. Okay.
Yeah, thank you. Right, because I mean, if you don't make contact, or if you do make contact with a de-energized state, it's the same result, right? So you want to make sure you're getting there. You're looking for a 0, and if you get a 0, it's great, unless you didn't make contact. So. Tap into a little bit of OSHA, right? Because that's more of the regulation. 70E is a best practice standard, right? An industry standard. That's a lot of content in there. A lot of smart folks went in there and developed that over the years and have been iterating every 3 years, right? But that's not the regulation. That's not what you have to do as an employer. So a couple quick blurbs in 70E, or sorry, in OSHA, 29 CFR 1910. De-energized parts, right? Live parts of which an employee may be exposed shall be de-energized before an employee works on or near them. Less than 50 volts, don't worry about it, but 50 to anything above 50, you gotta de-energize. And then second, a qualified person, going back to Caitlyn's statement earlier, it's a qualified person. It just can't be anybody that's authorized or anybody that's walking by. You got to be trained in this and how to do it and what it means. But a qualified person shall verify that the circuit elements and equipment parts are de-energized. So de-energized comes up quite a few times in OSHA, 29 CFR 1910. But what's the benefit of OSHA, right? It's the stick. It's what you have to follow, but it's the what. It's not necessarily the how. So the example I often use is you want to go on a vacation to a beach. That's great. That's the what. But how you actually get there, how long you're gonna spend, how much you want to spend, like all that isn't in OSHA. That's where 70E comes in. So the tie between OSHA and 70E really is that 70E was created at the request of OSHA, and OSHA supports its use, as you see my little quote down there at the bottom. Tom Galassi, he's retired now, but a former director in one of his standard interpretations, which I've got linked there if you wanted to check it out. He states that compliance with NFPA 70E is an acceptable means of hazard abatement. So 70E, while it's not a regulation, if it is being followed, it is a means to accomplish OSHA, which is a great point to have, right? You don't have to use 70E, but it's worth using it unless you want to come up with your own processes, which is a whole different level of effort.
Well, yeah, that's exactly right. It's like if you're not at least meeting the recognized industry consensus standard of 70E, which is out there and available for anybody to use, then you could, I mean, they do use 70E to support citations. They don't enforce it, but if you're not at least following that minimum, and I've talked about this so many times, it really is a minimum, because even if you follow it to the letter, you can still get hurt. That's a whole nother topic, but that is seriously the minimum guidelines, unless you can figure out how to reinvent the wheel for yourself.
Right, and do it better. As you point out, it's the minimum. So Caitlyn already touched on this a little bit. New for 2024 was at each point of work for the testing. I guess let me back up. So this is focusing on just that 7th step, steps 1 through 6 that we just covered a couple slides ago, as well as what Caitlyn covered. We're not going to touch on again very often. But that step 7, that testing step, the bread and butter, where you're actually confirming absence of voltage, that part was updated in the 2024 edition. Really just at each point of work was added. That at each point of work had been in the blurb for absence of voltage testers since the first iteration, and so we're just it's kind of improving the previous the verbiage as well. So 2 methods, right? Portable test instrument, and then now using the absence of voltage tester with the exception. It got to be installed in accordance with the manufacturer's instructions. Pretty straightforward. That's anything from a wire nut to a dishwasher. You have to install it based on how the manufacturer wants to do it, or says to do it, how it's designed. Absence of voltage testers are no different. It's got to be listed and labeled for the purpose of verifying absence of voltage, and what that means is it's UL 1436, which is the UL standard for a bunch of other stuff too, but absence of voltage testers are in that standard, and it gives lays out what an absence of voltage tester needs to do, what tests it needs to accomplish and be tested to by UL to be called an absence of voltage tester. So there's a whole other standard around there about what this product needs to do. And then steps 3 and 4 are more or less the bread and butter of that process. It's the automation of that step 7, right? You're testing phase to phase, phase to ground with this device, and it's got to test a known voltage source before and after. That's the core part of the process that absence of voltage testers automate. So that's the standard stuff, right? So now I do want to touch on a couple different products that are often used in these industrial manufacturing environments, right? To show presence of voltage, show absence of voltage, right? To do all that testing, because each one of them has value, right? But just different types of value. So portable test instruments, right? Great, they're portable, they're inexpensive, many uses beyond just absence of voltage testing. Troubleshooting, I've got 3 of them in my house, I think, and I'm not even an electrician. Very useful devices. Challenges, as Caitlyn pointed out, device rating, operation, stuff to use PPE, making proper contact, ergonomics of them. There's a lot of human error, a lot of choices that you need to make that goes into using that device. They're great for presence voltage testing and absence of voltage testing, because you can go through that process to ensure that they are functioning properly. So the only reason why absence of voltage testing is really great for those, because you can use those devices to go through that live process. Another product that are out there often that you see is permanently mounted indicators, right? These are passive devices that illuminate on the presence of voltage. Has its use, right? You want to know if that cabinet is energized? Great. You want to see if all 3 phases are energized? Great. Right? Quick visual for voltage presence. That's the pro. Hazard or challenges with them are that voltage, that hazardous voltage is typically brought to the back side of that device, which is on the panel door typically. And they lack a way to validate that the function of the device is working, right? You can't do a dead live test on them. And then they are permanently installed. So if you want to know 3 spots within an enclosure, you need to install 3 of these devices. So can add up price-wise, depending on how much information you're looking to get. They are typically used for presence of voltage, mainly again, because you can't validate that they are functioning properly. If a solder point came loose or blew a fuse or some sort of electrical component in the PCBAs that are inside of these devices, you can't verify that they're working properly. So that's why you can't use them for just absence of voltage testing, just because the lights go off. Think of a socket, right? A light socket in your house. Just because that switch is on and the light bulb's off doesn't mean it's safe to go in there and put your finger in that socket. Not that I would recommend ever doing that, but get the point, I think.
That's a good point. And I do appreciate that you're pointing out the difference between the indicators and the absence of voltage testers, because I've seen a lot of people get those confused, and they install a lot of indicators around thinking that, oh, well, the light's not on, so we're good to go. Right. And that's not really going to cut it.
Right, absolutely. And they serve a purpose, right? They're a great, cheap little device to show that there is voltage there. Just can't confirm that it's not there. A little bit of an inverse thinking sometimes. But so another product that you'll see out there a lot of times, and sometimes these will have lights as well, but they're test portals. So they're a point where you can measure and put your meter on them. Passive device, again, you can measure presence of voltage because you can only really tell if it's there. It's great because you can get those measurements with the door closed, right? You're not having to open that cabinet door and do those measurements, right? You can do that from the outside. So that is a pro for sure. Other challenges is just like the indicators, the hazardous voltage is brought to the back of that device, which is on the door. So you're bringing the hazardous voltage to the door. And again, just like indicators, they lack a way to validate that the function of that device is still working, right? You can't verify that it's connected properly. You can't verify that it's functioning properly still. And then just like indicators, permanently installed. So if you want to be able to have that measurement point on the outside of the panel in multiple places, you've got to install multiple of these devices. Again, because you can't verify that the device is working properly. Really just great for presence of voltage, absence of voltage, not so much. Another kind of similar product, right? I mean, power supply. If it's connected to power, would you verify absence of voltage through the outputs of that power supply? Probably not, right? That would be the power supply could have failed, not necessarily the line to the power supply. So that's one of the challenges with that product. And then come absence voltage testers. It's an active device that automates the absence of voltage testing process. So you don't have to open the panel door. That device is installed in the panel. We'll get more into that, I think, in the next slide. It's installed in the panel door. Don't have to open the door at all, and it performs internal and connectivity validation steps every time you push a button and initiate the test, it will verify that its own internal workings are performing properly, as well as it's still connected to the voltage source. Challenges, it's permanently installed. So if you do typically test for the absence of voltage in a few different spots within a cabinet, you do need to install an absence of voltage tester at each discrete location. So
that's a good point. We actually just had a question about that, Paul. If you have multiple sources to an electrical enclosure, like a drive enclosure, do you need two absence of voltage testers, one for the 480 volt and one for 120 volt from a separate source? So the answer is yes. Okay.
Yep. And it comes down to that point of work, right? If you're working at those different areas, then yeah, you would want to install multiple absence of voltage testers.
Makes sense.
Now, absence of voltage testers, both presence and absence, and they really, as the product based on UL 4236, really only need to test for the absence of voltage. Presence of voltage is commonly a convenience that it's added into the product because you're already attached to the lines. You might as well include that functionality as well. So they're commonly presence and absence voltage tests. Portable testers, right? So we're going to focus on those two absence of voltage methods, right? Portable testers, and Caitlyn touched on this a little bit earlier, inadequate ratings, exposure to hazards, right? You're having to enter that panel before you've confirmed its absence of voltage. And then human error is the biggest one, right? When you look at human error, and this goes beyond just safety processes, this goes for quality issues in assembly and production. That's why there's robotics and all these other automation processes, because human error causes problems, right? We are terrible at doing the same thing every time and getting the same result. We're going to do the same thing every time. We're just probably going to get a different result every so often because there will be little variances there.
Very, very good point. Actually, we're going to do the next webinar. The whole webinar topic is about human performance and how it's a risk.
Right. If human performance wasn't an issue, what, NBA, everybody would be shooting 3-pointers.
Oh my gosh, yeah.
And hit rate. So there's errors everywhere. So, and then with the meters, you've also got misinterpreted settings. Again, that's more of a human error. Potentially you're misreading it. The probes can be damaged, and you're supposed to be inspecting those, but they can still get damaged, and another thing to worry about. And then lack of contact, which Caitlyn touched on earlier as well, right? Those safeguards, touch safe things, which is all awesome, right? They're there for a purpose, for that incidental contact. But when you need to make contact, they prevent that, and they create an additional step that you have to work around. Getting into absence of voltage testers, right? What are they? I've got my demo here. If we have time, I can flip my screen around or flip my camera on and show you. But it is a permanently mounted device, right? We've covered that quite a few times. And what you see here is it's typically an isolated isolation module where it's permanently installed to the voltage source. In this case, a couple, 3-phase conductors. And then the hazardous voltage is isolated at the isolation module, which is why we call it the isolation module. From there, there's the system cable, which is just an Ethernet cable that is just connecting out to your HMI that's on the panel door, right? So when you got that panel door shut, what you see here is this device, and you initiate by pushing the button, and it sends a signal and kicks off the series of questions and tests that it's running on the system that it's permanently installed to. Common illuminations and things you'll see on the face of the indicator is red LEDs if everything's humming away and everything's energized. And then once you get an absence voltage confirmation, you'll get a green illumination here indicating that it is safe to enter. Comparing the two methods side by side in a very dumbed down, very simplified version, right? Compares to two tests. You got your tester and putting on your PPE. You're opening your panel, and at that point, because you're opening the panel and you haven't confirmed absence of voltage, you have to assume that hazardous voltage is still present, right? And then you go through and you test your tester, test the voltage, test your tester, do that live test, and you are exposed to electrical hazards. Caitlyn's example before was kind of a scary example, right? Is you got that panel door open and he was exposed to hazards. Thank goodness nothing happened. That typically takes 10-20 minutes, could be longer, could be shorter, right? All depends on the facility and a lot of other factors there. So with absence of voltage testers, it goes through and runs through all the series of tests from the outside with the panel door closed, and you're not opening that panel until you've already confirmed that there is no hazard present inside the enclosure, right? So at that point, there's no exposure to electrical hazards, no more than if you were just to walk by the cabinet with the door closed. That process really takes like 8 seconds, but we call it 10 seconds just for easy mental math there. Quite a bit of a reduction in time. Getting into exactly what happens when you push the button, because it's an electrical device, you push the button and you're trusting your life with it, right? It's a big thing. It's not like you're just flipping a light switch on and the light comes on. There are quite a few steps that it does that gives this the confidence, right? So when you push that button, it doesn't just check for voltage and it says it's safe or not. It goes through and confirms that there's enough power to perform the test, right? So battery indicators, it checks that the battery has enough life to initiate on the test all the way through. If it does not, it'll stop testing and fail. It goes through and checks the health of the circuit elements. So very much like when you turn on your computer, it goes through and checks all the communication between the motherboard and the hard drive and the RAM and all that. That's about the extent of my knowledge about that, but it goes through, and if it fails, it's going to give you the safe mode or give you an error that, hey, something's not right. VeriSafe does the exact same thing. And it goes through and makes sure that the threshold tolerance, the circuits are in place, and it's able to measure right around that 3-volt threshold, which is in UL 1436 as that safe or unsafe threshold. Then it checks the known voltage source. It verifies that it's connected properly. If it is, and then it verifies that the threshold that it measured is under 3 volts. And then it goes through and does that whole set of tests again. The only way you will get a green light is if it passes all 6 of those tests twice. If it fails any one of them, it fails the entire test and will not give you a green light. That's where we get that SIL3 rating. If you have a manufacturing issue and the resistor, a microcontroller inside the electrical component fails inside the device, it's going to fail that check health of key circuit elements. And at that point it fails and it's not going to give you a green light. What happens if that happens and if it fails? It's going to give you a flash code. It'll tell you, hey, something's not right. Something is not passing my set of criteria. Could be checking the battery. It could be, hey, the voltage is, still 120 volts, still 480 volts. Don't enter. Something's not right. Something's too hot. Couldn't verify the installation. That number of flashes right there, number 4. It'll flash back at you and at least give you the initial breadcrumbs of here's why you failed, or here's why I failed, more or less. And then you can go off and start figuring out, okay, well, now I need to troubleshoot. You might need to put on your PPE then if you need to go into the cabinet and do it the old-fashioned way, right? But it will not give you a green light if any of those criteria failed. That's essentially not happening. When you run through the SIL3 numbers, it's like if you were to test this, you run a test every hour for 11,000 years, that's the probability of you getting a failed result. So quite a long time, not happening in our lifetime. So where can you install VeriSafe, right? I'm not going to run through kind of those spec points on the left so much. Those are there for you to read through once you get the presentation later. But the key points I want to cover is max nominal voltage up to 1,000 volts. Cat 4 is up to 600 volts, so you can get into those service entrances, those 480 service entrances. Compatible systems, 3-phase, single-phase, AC or DC. We have all those compatibilities with VeriSafe. And C1, D2, and C2, D2 hazardous location ratings as well. And then safety and integrity level of 3, which I'll point out that portable meters don't have a SIL3 rating, indicators don't have a SIL3 rating, and others, the test stations don't have a SIL3 rating either, because it's just not a tested and designed product to the same level as an absence of voltage tester. Installation methods, how do you install this? Where does it go? So working left to right there, you install this not spanning line and load, not spanning devices. You do not want, well, I guess maybe let me back up. When you're installing a VeriSafe, you've got the 6 sensor leads and 2 ground. You've got 2 leads per phase, so that's the 6, and then 2 for ground. So you've got 8 total sensor leads coming off of there. Each pair of sensor leads for each phase should not span a disconnect or a device. They should be on the same side, line or load, not line and load. You don't want them to span the disconnect. But that's pretty much it. 2 mechanical separate discrete terminations, and then that can allow it to go and do its connectivity verification. You can terminate through our insulation piercing connectors that go anywhere from 14 American wire gauge to 500 MCM. If you use other insulation piercing connectors, you can integrate those with a terminal block. PDBs and power distribution blocks, multi-tap lugs, ring terminals if you're going to tap a bus, and then everyone's favorite, I'm sure, split bolt connectors, but you see those less and less now. So maintenance wise, if you use a battery indicator, a battery system, it's a 5-year life of that battery. And then the only other maintenance what we recommend is to inspect the gaskets and O-rings on the device to maintain your IP rating every year, so annually. If you see them cracking, just replace them, right? But most environments, that'll be many years before they start showing signs of wear. It's just if you're in, heavy environmental wear conditions like mining or other dirty environments that might cause them to dry out further. Sugar plants, I know, are pretty rough on O-rings and rubbers. So kind of the main value props of VeriSafe, right? First and foremost, it was developed to reduce risk and avoid those incidents, avoid that hazard or that exposure to the hazard. That was the first and foremost why it was developed. Kind of the benefits of and the outcome of that is it just does it quicker, right? It saves about 20 minutes, right? 19 minutes and 50 seconds if you're doing that mental math. Quite a bit of time to get you to get into that value-added work, because honestly, absence of voltage testing is not value-added. It saves lives, right? It creates a safe condition, but it's not getting you any closer to fixing whatever you're going in there. And then finally, it automates, right? So you're removing that human factor and removing that complexity. Because when you think about these different panels, no 2 panels are created the same, right? I guess I'll say that with a little caveat that there are redundant systems, a lot of similar panels, but they're all labeled differently. They're all, MCC buckets, higher or lower, hot environments, all that stuff increases complexity and creates hazards or potential for hazards. VeriSafe automates all that, right? So you don't have any of that. It's pushing the button the same time every time, and whether it's a high panel or a high bucket or a low bucket, you interact with it in the exact same way. So there's a lot of consistency there, which helps reduce complexity. So with that, thank you. 2018, VeriSafe was a product of the year. That was the first year that we were really getting steam, because that was the first year that NFPA 70E had absence voltage testers or permanently mounted devices written into an alternate. So it was a big year for VeriSafe.
Absolutely.
Want to learn more? I guess contact me. abon@panduit.com. Go through Caitlyn.
Yep.
She knows you can contact me as well. So
Absolutely. Thank you, Alan. Appreciate you going through that information. Definitely gave us a better look at not just, indicator lights, what they do versus test ports, and then actually what it takes to get the rating as an absence of voltage tester. And it really does. It saves a lot of time, but it also just it saves your chances of exposure. Those stories of people that get in and, oh, it actually is still energized. Well, you're not going to be surprised. You'll know ahead of time. So, all right, if you could give back control, and then that way I can go through the last couple things real briefly here.
You should have control now.
Perfect. It should be showing my screen. Fantastic. So I did have, just real briefly, whoops, there we go. What can you do to get started? Well, first off, train and qualify personnel, make sure they know how to actually establish electrically safe work conditions properly before removing PPE, if they're doing it by hand especially. And explore permanently mounted absence of voltage testers. Again, they're not required to be used, but clearly they can have a lot of benefits. So at least give it a think through, look at your equipment, maybe have a priority level list, things that are most frequently accessed and or highest hazards. I would say those are the places to start exploring these options. Do have a complete accurate system study, because that PPE they have to wear, if you don't have the absence of voltage testers especially, that's only going to be able to be determined if you know the severity of the hazards. And then of course supply the right PPE to make sure they're safe as they're verifying. And if you need some help, we've got you covered. Of course, Herzig Engineering can do the studies and the trainings and all sorts of other things. You can go ahead and reach out and we'll talk, we'll get you started. But understanding what's required and why is the first step to achieving compliance and, more importantly, safety. So we do have a couple questions coming up. I do just want to throw out another thank you to Alan for being on today and explaining what absence of voltage testers actually are, what it takes to be, classified as one, how they help, how they get installed, maintenance, all of that. And of course, like he said, if you want to learn more, you can feel free to reach out to him. Otherwise, my contact info is here as well. And now I'm going to go over to the questions. So I had somebody ask, what are other electrical safety standards other than 70E that support OSHA? So you had mentioned that it's, one of them, and it's honestly the best one. Some others that come to mind are like the IEEE. They have 3007.3, I believe. It's another electrical safety standard. It's not as updated, like nearly frequently enough. I think the latest edition was 2012, if I'm remembering right. There's also the NETA and ANSI and ASTM standards. There's the National Electrical Safety Code. That's more for medium high voltage utility kind of stuff. 70E is really the main one as far as electrical safety. Now, mind you, that's electrical safe work practices, like in a workplace. There are other NFPA codes and standards that they would refer to as well, like the National Electrical Code for installations. The 70B is now a standard for electrical equipment maintenance. There's specific electrical safety standards in a lot of other NFPA books as well, as far as like the actual enclosures, making sure that there's interlocks for certain types of equipment. There's a lot of standards out there, but as far as safe work practices, whenever you have to put on something and work on that piece of equipment, that human side of things, a lot of times we're looking at the 70E. And then the other question, so can we achieve an electrically safe work condition where it's not possible to attach a lock to existing disconnecting means? So that must be some pretty old equipment because, more recently OSHA does require anything to have a lockable point. So either we need to start looking at renovating and getting that adapted and retrofitted for a lockable disconnecting point, or you have to get a little bit creative and find another way to remove that contact point and make it impossible for it to be turned back on. So that might be a little bit more discussion than we have today to go through, kind of a different topic too. It's a little bit more into the lockout tagout standard and how to get your equipment up to date with that. But establishing an electrically safe work condition, yeah, it's an OSHA thing, not just 70E for sure. To get an electrically safe work condition, you would have to somehow physically make it impossible for someone to accidentally turn it back on. Okay, so if there are any other questions, please feel free to submit them. I know we're going just a few minutes after the hour here, but it was a lot of really good information. So thank you so much for attending. If you need to hop off, I totally understand. You will be getting an email with the PDF of these slides, both Alan and my slides, and so you can reference them if needed. The recording will be posted on YouTube later today or early next week. We'll see how my day goes. So thank you all so much for attending, and we'll stick around for a couple minutes to answer questions, but otherwise, go home safely.
Yeah, have a good weekend.